Welcome to the Flownex webinar series. Today's industry is hydrogen. Today's speaker is Leander Klein. Leander is a thermal fluid simulation engineer specializing in renewable energy and propulsion systems.
Thank you, Marinus. Welcome to today's exciting webinar, where we will discover how Flownex can be used to solve some of the world's toughest problems. For today's agenda, we will be looking at the PEM fuel cell, its system components, why system simulation is so important, what Flownex is and how it can be used in the design process, modeling critical paths of the fuel cell system, and show how full transient simulations can be achieved with minimal effort. I hope you are ready. The PEM fuel cell. There are several fuel cells being researched and in use today. The operating principles are the same, however. They are developed to take advantage of different electrolytes and serve different applications. In today's webinar, we will be looking specifically into the PEM fuel cell that uses a proton-conducting polymer membrane as the electrolyte. Typically, this fuel cell will use hydrogen as a fuel, and they have several advantages over other fuel cells. One being that it operates at lower temperatures, usually at around 80 degrees Celsius. This means that it can start up quickly because less warm-up time is needed. It also has a high power density and is low in weight. The fuel cells used in electrical vehicles, for example, are most commonly the PEM fuel cell. Fuel cells transforms chemical energy through an electrochemical reaction of hydrogen and oxygen into electrical energy. Hydrogen is supplied to the anode side of the fuel cell, where it is being catalytically split into hydrogen ions or protons and electrons, as seen in this half reaction. This is known as the oxidation half cell reaction of the hydrogen. The protons being formed in this reaction then permutate through the special polymer electrolyte membrane and move to the cathode side. The electrons created in the half reaction is prevented to move through the membrane and is forced through a conductor. And as we all know, the flow of electrons is known as current. At the cathode side, where air is being supplied, the oxygen will react with the hydrogen ions when the electrons has also successfully reached the cathode. This can be seen by this half reaction, presented by this equation, where the oxygen in the air reacts with the protons moving through the membrane and the electrons that moved through the conductor to form H2O or water. The overall reaction of the fuel cell can be seen in this equation, which is hydrogen plus oxygen gives you water. This highlights why so much focus is put on the development of fuel cells. It is essentially a power source with no carbon or harmful emissions, only water. This in contrast with, for example, the combustion of gasoline with the reaction as seen here, where carbon dioxide, the primary greenhouse gas emitted by human activities, is one of the products. The PEM fuel cell is one of the best viable alternatives for cleaner energy source. However, operating this fuel cell comes with quite a few challenges. One being that the membrane must be hydrated properly to allow for ions to conduct. But if water condensate and form droplets, it can restrict the flow channels and reduce the ionic conductivity. This is called flooding. So essentially, the PEM fuel cell, to perform optimally, the system needs to be designed such that the electrolyte is well humidified. This means that water management is extremely important during the operation of the fuel cell. In the PEM fuel cell, the operating temperature is quite low compared to other conventional fuel cells. However, heat is being generated during the chemical reaction process. If this heat is not properly removed, the fuel cell stack temperature will increase, which will essentially damage the electrolyte and decrease the rate of proton movement. This means that proper thermal management of the fuel cell stack is necessary to ensure high performance. To keep the membrane at a certain temperature and keep the moisture content of the membrane such that it does not dry or flood, several components need to be added to the system. A simplified model of the PEM fuel cell system components needed for proper water and thermal management is shown here. Gaseous hydrogen is stored in a high pressure tank. The flow rate is controlled with a valve and then fed into a heater to increase the temperature to the desired stack temperature. On the air side, a few more components are needed to control the water content of the air entering the fuel cell stack. As air is taken from ambient conditions, a compressor is needed to achieve the desired operating pressure. A heater is then again also added to increase the temperature. The ambient air does already have a certain amount of water content and is at a certain relative humidity. However, it might not be sufficient for the polymer electrolyte membrane to operate efficiently. A humidifier is added to the network to control the water content at the cathode side. When the overall reaction of the fuel cell occurs, water forms, and thus more water will exit the cathode than the water entering it. A condenser is used to cool down the airstream, allowing for the water vapor to condensate. This liquid water can then also be used in the humidifier and the rest be discarded to the atmosphere. The water and thermal management requirements for the PEM fuel cell requires the addition of several components in the system. These components need to be designed and optimized to ensure that the required performance is reached. Using a system simulation approach will aid the engineer to model the system components, design them, optimize them, and understand the component behavior of the entire system. So typically the requirements for a system simulation would be fluid capabilities such as complex gas mixtures of humid air, chemical reaction models for the fuel cell stack, pumps and compressor models, discrete sized heat exchange models, typical pressure drop models such as piping, valves, and so on, steady state and transient solving capabilities, and then finally control models for transient simulations such as PID controllers. So, where does Flownex come in? Flownex is an engineering tool that can be used by engineers in the design and analysis process of thermofluid systems. It solves the fundamental physics for flow and heat transfer components of large thermofluid systems. Flownex houses a large library of standard components used in industry, advanced fluid models, control library, and integration with third-party software such as ANSYS, MATLAB, and Simulink. Ensuring for the best standards of quality compliance, Flownex is developed within an NQA1 and ISO 9001 environment. Flownex also has a user-friendly interface with a help manual conveniently accessed using the F1 button. Flownex uses a one-dimensional approach in solving systems. Flownex does this by solving the conservation equations of mass, momentum, and energy on component level. All components can be solved just fundamentally in true steady state as well as transient with either fixed or adaptive time steps. In summary, Flownex can be used to run a steady state and transient simulations where flow is predominantly in one direction and with heat transfer in two dimensions. It simulates system behavior from physics on component level. Back to the typical requirements for simulating a PEM fuel cell. Flownex gives you the capability of using compressible gases, two-phase fluids, mixtures, and so on. Custom fluids can be created or imported directly from NIST, which can come in quite handy if you want to use a specialized fluid or want to evaluate the fluid in a temperature or pressure which is not included in the custom fluids in Flownex. Flownex can also give you the ability to model the physics in a fuel cell. To include this is very important to understand the behavior of the system components with the fuel cell model included. Flownex already has a built-in CEA chemical reaction component to calculate chemical reactions. Custom reactions can be implemented using scripting languages such as C#, Ease, and Python. Flownex can also be integrated with other software packages such as Cantera and MATLAB to realize the behavior of the fuel cell stack. Flownex also allows you to import reduced order models or ROMs using the Flownex FMI capabilities. There is also a large library of components including simplified models for pumps and compressors, where you can design the component for a fixed mass flow rate. Complex models for pumps and compressors are also included, where pump charts and compressor maps can be included as well. Flownex also houses different heat transfer models such as common geometries, fin tube heat exchangers, plate heat exchangers, and so on. Flownex also allows for custom correlations for heat transfer to be included. Typical pressure drop models such as pipes, valves, and so on can also be included in Flownex. This ranges from basic to complex models if specific data is available. Flownex also allows for steady state as well as transient solving, including an implicit transient solver, which allows for very large time steps for long transient. Lastly, Flownex includes a large library with analog and digital controls. So, now that we know what Flownex is and what it is capable of, let's see how Flownex will be able to help engineers to design the systems of a PEM fuel cell. Here we can see the PEM fuel cell together with all the necessary components. On the left hand side we can see the hydrogen side, and on the right hand side is the air side with all its components. I'm sure you would like to know much more about this model, but before we get into it, let's just see how the thermal management system can be easily and quickly modeled inside of Flownex. So, as we said, the thermal management system of the PEM fuel cell is quite important. So let's see how we can use Flownex to essentially calculate and design and model a thermal management system that would typically be found on a PEM fuel cell. So essentially, the Flownex, as it's presented now, allows you to have different ribbons, essentially with different inputs that the user can specify, different tasks, abilities to couple to third-party applications. And then here on the left-hand side, we do see a lot of the properties of the components, and also the drawing pages, and on the bottom we do see our flow solver conversions, and on the right hand side we have the options of different components, charts and lookup tables, and then solver settings. So Flownex really do give you quite a lot of options in designing a system. So essentially, we are looking at the thermal management system of a fuel cell. As we said, there's some heat being generated during the reaction of the fuel cell in the fuel cell, and essentially we need to extract that heat by means of ambient air blowing through channels, or liquid water moving through channels. So essentially we can start dragging in components for the fan. So for example, the fan will be represented in this case by the basic centrifugal pump. Essentially this we do have a specific component for the fan. However, this does give the user the ability to design for the specific head and flow required for that specific fan, and then essentially that user can then go and choose on fan graphs essentially which fan would be appropriate for this system. We can then also drag in a pipe component, and this will represent the channels, the flow channels essentially, that would contribute to the extraction of that heat. Then next we can specify the boundary conditions, and this will essentially realize the inlet and outlet conditions for the thermal management system. So we can specify at the inlet the pressure, let's say it's ambient at 100 kPa, and then the temperature we can say it to be standard at 25 degrees Celsius, and then the exit conditions, let's specify it as 100 kPa as well. Then let's realize and include the geometry for the flow channels. We can specify it as 0.5 meters, and this typically does depend on your specific thermal management system's geometry. The length is 0.5 meters, and let's give it a small for one channel as 5 millimeters, and then a roughness of these pipes being around 30 micrometers. And we have approximately, let's say, 100 channels in parallel. We can then also specify the fluid, and in this case we do have a pure fluid, gas, and we can say air. So this is defined. The two nodes, the two boundary conditions is defined. Now we do have to realize or include the heat transfer, and we can use this composite heat transfer element, which can handle conduction, radiation, convection, and we can just align it here. So it's always better to work in a much neater network. We can then also just add in the a node for this point here. So essentially the heat being generated in the fuel cell will be added to the thermal management system here. Let's say just 500 watts in this case. And then essentially we can then define the geometry for the heat transfer. We can specify the conduction area as using a downstream pipe. We can add in a conduction layer, and we can specify it as 1 millimeter. And then the material we can specify as aluminium, which will be under metals, pure aluminium. And then we did specify the conduction. For the convection, the heat transfer option for the upstream will be adiabatic, and then the downstream will be convection, and essentially calculate the convection coefficient. And let's say for this example we will use Dieter's Bulter. So essentially the temperature of the fuel cell stack, which we are quite concerned of to have a constant temperature, will be represented by this node's temperature, for example. So we have to define the nodes, the boundary conditions, the flow channels, the heat transfer element, and then also the heat being generated. And then lastly, we can design for the fan, and essentially we can fix the mass flow and change for design. So we are going to design this component, and let's start at 10 grams per second. And then essentially we want to apply a reference chart, and let's just give it an efficiency of 0.8 at BEP, or the best efficiency point. And let's see what our temperature is on this point. So currently our fuel cell is at 83 degrees Celsius, which is quite close to, let's say we want to keep it what it's typically at, which is 80 degrees Celsius. So what we can do, Flownex does give you the ability to design for a certain condition, and I've already set up a designer configuration. And let's just redo this. We essentially want to keep this node, which is node 18. We can specify node 18 and its temperature, and we want to define it or get it as 80 degrees Celsius by changing this components and the centrifugal pump number 10. It's a fixed mass flow rate, so we can just specify the mass flow, and let's just vary it between 8 and 12 grams per second. Just make sure it is active, and we can then just run the designer, and then essentially Flownex will automatically calculate what mass flow rate we do need to get 80 degrees Celsius. We can then take this off. So essentially the head is designed, the flow is designed, and now finally we can add in a control system. So this is the advanced PID. Essentially this has already been calibrated for the specific K proportional term, the integral time constant, and derivative time constant. And more information on control can be seen on some of the webinars present on the Flownex website. So essentially we want to add in a data transfer link. So essentially this is the process value. So that's the 80 degrees Celsius, and this will go to the process value. We can just drag it in here, and then we want to drag in the output to control the speed ratio. So essentially the output will be dragged to the speed ratio, and then lastly we can graph the results that is necessary. So we do have a couple of options for the graphs, and for example we can use the line graph and essentially plot the output, and then just plot the output and essentially the process value as well. Okay, we can also align this quickly using the tool available in Flownex, and then this should essentially keep the temperature at 80 degrees Celsius. So let's just solve it once more, and let's just run it. So essentially we have put it we've put the set point at 80 degrees Celsius, and we can, let's just do multiple y-axes, and essentially we can see how the PID is searching for 80 degrees Celsius by changing the speed ratio. For example, the upper limit has been defined as too little. We can just increase this to 2, and then essentially this will make it much easier to essentially find that 80 degrees Celsius. So there you have it. It's quite easy and simple to calculate the thermal management system of a PEM fuel cell, and then also apply the control for that fuel cell. So back to the PEM fuel cell and its system components. Now that we have simulated the thermal fluid, the thermal management system of the PEM fuel cell, this can be implemented into the entire model to essentially extract the heat being generated from the reaction inside of the fuel cell. Essentially, here we can see the hydrogen side. So essentially this consists out of the tank, the high pressure tank for hydrogen, a valve, and then the heater being realized by this flow resistant to essentially get the temperature or the required temperature of the fuel cell stack. So essentially this is at 80 degrees Celsius for this particular example. On the right hand side we have a quick script which essentially calculates the mass fractions of all the components of humid air, such as the water, the nitrogen, the oxygen, and so on. So essentially that's needed for the chemical reaction inside of the PEM fuel cell. We have the compressor here being resembled by the basic centrifugal pump, and we have another heater here just before the humidifier, and this is a custom component that has been created for this specific conditions. And essentially we have a dehumidifier or the condenser, essentially cooling down the airstream to condense a certain amount of water, and this was also done through the use of a custom component. So essentially when we look inside of the PEM fuel cell, so this is just one example of how we can realize the physics and the behavior of the fuel cell stack inside of the simulation model. For this case, we've added a script which captures all the complex physics inside of the stack, but this can also essentially be coupled to third-party software such as MATLAB, Simulink, and which essentially you can pick from different types of fuel cell stacks and how they essentially behaves. So just to give you a quick overview, the hydrogen moves into this side. There's a certain amount of hydrogen ions or atoms being pushed through the membrane and then is added to the flow on this side here. Essentially then we feed this to our CEA Gibbs reactor, which essentially creates the chemical reaction for the fuel cell, and then we do have a creation of more water during this fuel cell reaction. So we can during this chemical reaction we do have a generation of heat, as we spoke about earlier, and here we can see the implementation of the thermal management system for this PEM fuel cell. So we can say solve this steady state, and essentially we will get the required solutions for the input parameters. So now what makes Flownex very, very useful is that we can understand the system from a transient perspective. So we can then run the system. So you can note here on the left hand side that the stacked power is being set to, in this case, 2.5 kilowatts. So essentially what will happen is when we specify 2.5 kilowatts, the fuel cell stack calculates the required hydrogen as well as airflow rate that is required, and this will then control this valve as well as this compressor here on the right hand side to get the required flow rates. so that you do not have a under or over too little or too much of hydrogen compared to your oxygen in the air side. So here on the right hand side we can see the this compares the sensed volume flow rate of the air on the right hand side and then the required airflow rate, and you can see that it is converging to become similar as would be expected. So then we can change the required power that this fuel cell needs to essentially deliver, and then the fuel cell will then start to change according to that requirement. So let's make it 0.6 kilowatt. You can see it's already going up here. You can see there's an initial spike, and then this will slowly increase until the required 2.6 kilowatt is reached. And similar here on the air side, the required air has been increased and the sense flow is also increasing as this compressor's speed is being changed to essentially realize that required airflow. So from a behavioral perspective, this is very important to understand how the fuel cell will react, and Flownex makes it so easy, makes it very easy to understand the behavior of such a system, and essentially a more detailed design can then be implemented using this model and the to essentially meet the requirements of a specific application. So here on the right hand side we can see how the required and the sense flow has become the same value, and we have reached the 2.6 kilowatts that has been desired. Flownex is a tool that can be used by engineers to design, optimize and evaluate thermal fluid systems. In the case of the PEM fuel cell, where the thermal and water management of the stack is extremely important, Flownex provides a way of understanding the behavior of these systems. It should be noted that this was only a basic example of Flownex's capability, and that further development can be done. For example, different types of cooling strategies can be investigated and compared to find the best performing solution. Instead of using air as a fluid, we can possibly investigate a closed loop thermofluid system using liquid water. We could potentially also investigate different system layouts and understand from a performance and efficiency perspective which one will be better. Flownex gives you the ability to complete a full system design. It can handle any complex fluids and gives you the ability to include custom fluids as well. It can also be used to simulate the chemical reactions within a PEM fuel cell using different models, and allows for coupling with external software. It includes a large library of components which ranges from basic to more complex models. It also gives you the ability to create your own custom components. Flownex also has numerous heat exchange models from basic to more advanced. It also includes various pressure drop models such as piping, valves and so on. Flownex allows for steady state and transient solving, allowing you to understand the behavior of the system in its entirety. Flownex is a useful tool for engineers in the designing and analysis process. As more emphasis is put on a cleaner, zero emissions world, the design of cleaner energy solutions has become imperative. Using a system simulation software such as Flownex will allow for rapid design of such systems, saving on cost and time. And this brings me to the end of this exciting webinar episode. I hope that you have enjoyed it as much as I did. If you have any inquiries or want to reach out to us, you can just send us an email at sales@flownex.com. Alternatively, you can have a look at our website for more details on Flownex and its applications.